Good morning, my dear students. So, in previous class, we see the introduction of performance of transmission lines, how the transmission lines are classified in terms of short transmission line and also medium transmission line and long transmission line. So, we discussed one by one short transmission line, that vector diagram, that analysis we see. So, performance of single phase short transmission lines. So, the capacitance of short lines is negligible and usually not considered. Therefore, only resistance and inductance of lines are considered. The first one and main point in short transmission line, there is no capacitance effect in transmission line. So you see please observe the diagram carefully. There is no capacitance effect. They have only resistance and also inductive reactance. So inductive reactance XL is nothing but 2 pi FL. So already I told that in introduction in unit 1, resistance and also inductance are in series elements. Capacitance is a shunt element. Capacitance lies in between two transmission lines, resistance and inductance in series elements. So we represent neatly the resistance and also inductive reactance, also load. So next point is the equivalent circuit of single phase short transmission line is shown in figure. The equivalent circuit. So equivalent circuit means all the parameters are lies in the diagram. Here, the line resistance and inductance are shown as lumped or concentrated instead of being distributed. So already I discussed, so which is the lumped elements, which are the distributed elements. In short and medium, we consider that is a lumped elements, which is possible physical separation. So in long transmission line, we assume the parameters are distributed. So please see the diagram. So Vs is a sending end voltage. Vr is a receiving end voltage. So current I. So here very important point is there is no capacitance effect in transmission line. So definitely there is no charging current in between two conductors. The sending end current is equal to receiving end current, means all the currents are same in short transmission line. Is is equal to IR is equal to I. The total currents are same. So but in case of medium and long transmission line, there is a capacitance, so the sending end current is not equal to receiving end current. But in short transmission line, please observe carefully, the sending end current is equal to receiving end current because there is no deviation presence, no deviation. This is a current flowing from sending end to receiving end current. Resistance element, inductive reactance element, we connect one load, sending end voltage and also a receiving end voltage. For this circuit, we draw the vector diagram. How can you draw the vector diagram? So first we taken Vr as a reference quantity. First one. So Vr is a reference. Take Vr. For simplicity, we can draw this one. But Vr reference means there is a horizontal component. No problem. So for representation, for a good diagram, we take as a Vr reference, just like as Vr reference. So O to or 0 to A. 0 to A represent Vr, receiving end voltage, or O, whatever it is, O or 0. Vr is a receiving end voltage, taking the reference. Once in any diagram, Vr is taken as a reference. What is the means of reference? Vr at an angle 0 degrees. The vector diagram starts from Vr. So what is a lagging? What is a leading? So lagging in terms of VR is a reference. Lagging is nothing but clockwise. There is, if you put the clockwise, VR is a reference. If you put the clockwise, that is a lagging. Leading means VR is a reference by putting anti-clockwise. Anti-clockwise, that is a leading. You must know these points. We are lagging and we are leading. So current I, we draw the current I, lagging or leading. Tell me. So this is a VR. VR is a reference quantity. In clockwise, current I is present. So definitely this is a lagging. So every time we represent the current IR is a lagging quantity. Why? Because we using all loads are inductive loads. So inductive loads mean definitely there is a lagging power factor. In case of the capacitive load, definitely we represented in leading power factor. So, but all electrical loads we using is a lagging. Lagging means we using the inductive loads. So first we draw the VR and IR or I, because all currents are same here. IR or IS or I. VR and IR. How can you draw the IR at an angle of phi r? At an angle of phi r. So what is the phi r? Receiving in phase angle. So cos phi r is a receiving in power factor. Phi r is a receiving in phase angle. So at an angle of phi r, we draw the current I. Okay. So voltage and also current finish. Next one is how can you withdraw the drops? So what are the drops present in short transmission line? So there is a two drops, one drop due to the resistance and another drop due to the inductive reactance or inductance. So here the current flowing in resistance is R, so the drop is IR, and also here the inductance, the drop is IXL. So how the drop is represent means, so resistive drop always in phase or parallel to the receiving end current, always parallel. So if there is a receiving, how to draw the resistive drop? Always parallel. The in phase means the current will flow, current direction is just like current direction is this one, definitely receiving in current also this. Next one is how can you draw the inductive reactance drop? So inductive reactance drop always 90 degrees from the resistive drop. So resistive drop always parallel to the current, receiving in current. Inductive drop always 90 degrees from the resistive drop. So finish. So in this diagram VR, IR, IXL. So how can you get the sending end voltage? The sending end voltage is the sum of or vector sum of receiving end voltage VR plus IXL plus IR. We get the sending end voltage clearly. So it's a simple analysis. So the sending end voltage, how can you get sending end voltage Vs? So we get the sending end voltage Vs is equal to VR plus resistive drop plus reactive drop, VR plus IR plus IXL simply gives the sending end voltage. So in the point representation OED, horizontal component, vertical component DBC, hypotenuse O to C. So O to C is sending end voltage, O to A is receiving end voltage, A to B is nothing but IR, B to C is a IXL. So O to E is a horizontal component. So in horizontal component, the magnet O to A is a VR. So how can you represent the horizontal component O to E? Definitely horizontal component represent in terms of cos. So this O to E is a VR cos phi R. Similar manner, dB is a vertical component. Who can represent the vertical component? VR sin phi R. Horizontal component cos phi R, vertical component sin phi R. We can easily finding the sending end voltage by using the vector diagrams. Once again I repeat. So first we taken as VR as a reference quantity. So we drawing the current IR. How can you draw the current IR? At an angle of phi r, we draw the current IR. After drawing the current, so the resistive drop always parallel to the current IR, always parallel to the current. Inductive drop 90 degrees from the resistive drop. So the vector sum of VR plus IR plus IXL is the sending end voltage. Receiving end voltage and also current phase angle difference is phi r, and also sending end voltage to current, there is a phase angle of phi s. Phi s is nothing but sending end phase angle. So cos phi s is the sending end power factor. Phi s is the phase angle in between Vs and I. Here the very important notable point is all the currents are same. Sending end current is equal to receiving end current is equal to I, because the capacitance effect is negligible. So this is the representation. I is load current, R is equal loop resistance, either resistance of both conductors, XL is equal to loop reactance, VR is equal to receiving end voltage, cos phi R is equal to receiving end power factor, which is a lagging. Already I told that lagging, because all the loads are inductive in nature, that is a lagging. Vs is equal to sending end voltage, cos phi s is equal to sending end power factor. So how can you find out the sending end voltage? Please see, the sending end voltage is equal to OC square is equal to OD square plus DC square. Please observe the diagram carefully. So we want to find out O to C. OC square hypotenuse. OC square is equal to, so horizontal components OE plus ED. OE plus ED. So vertical component simply DB plus BC. Here VS square is equal to OE plus ED whole square plus DB plus BC whole square. So substitute the magnitudes, we can easily find out the sending end voltage. So here OC square is equal to OD square plus DC square. What is the OD? OE plus ED whole square plus what is the DB? What is the BC? Substitute all the magnitudes. OE is nothing but VR cos phi r, that is a horizontal component. ED is directly the magnitude having IR. VR cos phi r plus IR whole square plus dB vertical component, that is a VR sin phi r plus BC. The value of BC is inductive drop IXL whole square. So Vs is equal to, OC means Vs. Vs is equal to root of VR cos phi r plus IR whole square plus VR sin phi r plus IXL whole square. So another formula is there for sending end voltage, that is a approximate drop. Approximate drop is nothing but sending end voltage Vs is equal to VR plus IR cos phi r plus IXL sin phi r. So maximum we using the approximate drop. Once again I repeat, approximate drop Vs is equal to VR plus approximately equal to Vs is equal to VR plus IR cos phi r plus IXL sin phi r. So both formulas we using for numericals. So maximum we using for simplicity approximate voltage drop, that is the Vs is equal to VR plus IR cos phi r plus IXL sin phi r. So percentage voltage regulation. So percentage voltage regulation, what is the voltage regulation formula normally? The change in voltage from no load to full load in expressed as full load voltage into 100. So change in from no load to full load, here Vs, change in from no load to full load, Vs minus Vr by Vr into 100, change in volt. Normally the formula for percentage voltage regulation exactly is Vs by A. So A is a ABCD constants. So there is a proof for that one. So I can show in next classes. So percentage voltage regulation normally Vs by A minus Vr by Vr into 100. But in short transmission the constant A value is 1. That's also derived in next classes. So whenever the constant A magnitude 1, the percentage voltage regulation becomes Vs minus Vr by Vr into 100. Similarly, sending end power factor cos phi s is equal to OD by OC. What is the OD value? Vr cos phi r plus IR. OC value Vs. Power delivered is equal to Vr I cos phi r. Percentage transmission efficiency Vr I cos phi r by Vsi cos phi s into 100. Finally, Vr I cos phi r plus Vr I cos mean output by output plus losses. Vr I cos phi r plus losses into 100. Losses is equal to I square R. So the vector diagram we take as the vector how to representation of vector diagram. Please see Vr is equal to Vr at an angle 0. 0 is nothing but Vr as a reference quantity. In vector diagram Vr plus J0. So current I is always lagging. So I is equal to I at an angle minus phi r. So that will represent I whenever that is a lagging, that is equal to I of cos phi r minus J sin phi r. This is standard. Any diagram we can represent that one. I lagging means that can be represent I at an angle of minus phi r, that is equal to I of cos phi r minus J sin phi r. What is the phi r? Receiving in phase angle. Z is equal R plus JXL. Impedance in a short transmission they have two elements, resistance and inductive reactance. Z is equal R plus JXL. Vs is equal to Vr plus Iz. So substitute Vr and Iz we get. So sending end voltage Vs is called Vs at an angle of phi s. This is a vector representation. So this is a analysis of short transmission. While taking the medium transmission line, the capacitance of the line is uniformly distributed over its entire length. However, to make the calculation simple, the capacitance of the system is assumed to be divided up in lumped or concentrated form of capacitors across the line at one or more points. The most common methods of representation of medium transmission lines are end condenser method, nominal T method, nominal pi method. So one by one we discuss in later. Thank you.